Chapter 9, Midlatitude Cyclones. The winter of 1992–1993 came to a stormy conclusion in eastern North America during a weekend in mid-March. The daffodils were already in bloom across the south, and people were thinking about spring when the blizzard of '93 struck on March 13 and 14. The huge storm brought record-low temperatures and barometric pressure readings, accompanied by record-high snowfalls from Alabama to the maritime provinces of eastern Canada. The monster storm, with its driving winds and heavy snow, combined the attributes of both a hurricane and a blizzard as it moved up the spine of the Appalachians, lashing and burying a huge swath of territory. Although the atmospheric pressure at the storm's center was lower than the pressures at the centers of some hurricanes and the winds were frequently as strong as those in hurricanes, this was definitely not a tropical storm, but instead a classic winter cyclone. After completing this chapter, you should be able to compare and contrast typical weather associated with a warm front and a cold front. Explain the concept of occlusion and the weather associated with an occluded front. Describe the Norwegian cyclone model. Outline the stages in the life cycle of a typical mid-latitude cyclone. Describe the weather associated with the passage of a mature mid-latitude cyclone when the center of low pressure is 200 km north of your location. Explain why divergence in the flow aloft is a necessary condition for the development and intensification of a mid-latitude cyclone. List the primary sites for the development of mid-latitude cyclones that affect North America. Describe blocking high-pressure systems and how they influence weather over the mid-latitudes. Describe the weather associated with an occluded front over the north-central United States in winter. Explain the conveyor belt model of a mid-latitude cyclone and sketch the three interacting air streams, conveyor belts, on which it is based. In previous chapters we examined the basic elements of weather as well as the dynamics of atmospheric motions. Our knowledge of these diverse phenomena applies directly to an understanding of day-to-day weather patterns in the middle latitudes, Figure 9.1. For our purposes, middle latitudes refers to the area of North America roughly between southern Alaska and Florida, essentially the area of the westerlies where the primary weather producer is the mid-latitude, or middle latitude, cyclone. These are the same weather phenomena that weather reporters may call a low-pressure system, or simply a low. Because weather fronts are the major weather producers embedded within mid-latitude cyclones, we will begin our discussion with these basic structures, Figure 9.2. Frontal weather. One of the most prominent features of middle latitude weather is how suddenly and dramatically it can change, see Figure 9.1. Most of these sudden changes are associated with the passage of weather fronts. Fronts are boundary surfaces that separate air masses of different densities, one of which is usually warmer and contains more moisture than the other. However, fronts can form between any two contrasting air masses. When the vast sizes of air masses are considered, the zones, fronts, that separate them are relatively narrow and are shown as lines on weather maps. Generally, the air mass located on one side of a front moves faster than the air mass on the other side. Thus, one air mass actively advances into the region occupied by another and collides with it. During World War I, Norwegian meteorologists visualized these zones of air mass interactions as analogous to battle lines and tagged them fronts, as in battlefronts. It is along these zones of conflict that mid-latitude cyclones develop and produce much of the precipitation and severe weather in the belt of the westerlies. As one air mass moves into the region occupied by another, minimal mixing occurs along the frontal surface. Instead, the air masses retain their identity as one is displaced upward over the other. No matter which air mass is advancing, it is always the warmer, less dense air that is forced aloft, whereas the cooler, denser air acts as a wedge on which lifting occurs. The term overrunning is applied to the process of warm air gliding up and over a cold air mass. There are 5 basic types of fronts: warm fronts, cold fronts, stationary fronts, occluded fronts, and drylands. Warm fronts. When the surface position of a front moves so that warmer air invades territory formerly occupied by cooler air, it is called a warm front, figure 9.3. On a weather map, a warm front is shown by a red line with red semicircles protruding into the area of cooler air. East of the Rockies, warm fronts are usually associated with maritime tropical, MT, air that enters the United States from the Gulf of Mexico and glides over cooler air positioned over land. The boundaries separating these air masses have very gradual slopes that average about 1 to 200 height compared to horizontal distance. This means that if you traveled 200 kilometers ahead of the surface location of a warm front, the frontal surface would be 1 kilometer overhead. As warm air ascends the retreating wedge of cold air, it expands and cools adiabatically. As a result, moisture in the ascending air condenses to generate clouds that may produce precipitation. The cloud sequence in figure 9.3a typically precedes the approach of a warm front. The first sign of the approaching warm front is cirrus clouds that form 1,000 kilometers or more ahead of the surface front. Another clue that a warm front is approaching is provided by aircraft contrails. On a clear day, when condensation trails persist for several hours, you can be fairly certain that comparatively warm, moist air is ascending overhead. As the front nears, cirrus clouds grade into cirrostratus that gradually blend into denser sheets of altostratus. About 300 kilometers ahead of the front, thicker stratus and nimbostratus clouds appear and precipitation often commences. Because warm fronts have relatively gentle slopes, the cloud deck that results from frontal lifting covers a large area and produces light to moderate precipitation for an extended duration, figure 9.4. However, if the overriding air mass is relatively dry, low dew point temperatures, there is minimal cloud development and no precipitation. During the hot summer months when moist conditionally unstable air is often forced aloft, towering cumulonimbus clouds and thunderstorms may occur, figure 9.3b. As you can see from figure 9.3, the precipitation associated with a warm front occurs ahead of its surface position. Therefore, any precipitation that forms must fall through the cool layer below. During extended periods of light rainfall, enough of these raindrops may evaporate for saturation to occur, resulting in the development of a stratus cloud deck. These clouds occasionally grow rapidly downward, causing problems for pilots of small aircraft that require visual landings. 1 minute pilots may have adequate visibility and the next be in a cloud mass, frontal fog, that has the landing strip socked in. Occasionally during the winter, a relatively warm air mass is forced over a body of sub-freezing air. This occurrence can create hazardous driving conditions. Raindrops become supercooled as they fall through the sub-freezing air. Upon colliding with the road surface, these supercooled raindrops freeze to produce an icy layer called freezing rain or glaze. With the passage of a warm front, temperatures gradually rise. As you would expect, the increase is most apparent when a large contrast exists between adjacent air masses. Moreover, a wind shift from the east or southeast to the south or southwest is generally noticeable. The reason for this shift will be explained later. The moisture content and stability of the encroaching warm air mass largely determine the time required for clear skies to return. During the summer, cumulus and occasionally cumulonimbus clouds are embedded in the warm unstable air mass that follows the front. These clouds may produce precipitation, which can be heavy but is usually scattered and short in duration. Table 9.1 shows the typical weather conditions that can be expected with the passage of a warm front in the northern hemisphere. Cold fronts. When cold air actively advances into a region occupied by warmer air, the zone of discontinuity is called a cold front, figure 9.5. On a weather map, a cold front is shown by a blue line with blue triangles protruding into the area of warmer air. Air near the surface of a cold front advances more slowly than the air aloft because of friction. As a result, cold fronts steepen as they move. On the average, cold fronts are about twice as steep as warm fronts, having slopes of perhaps 1:100. In addition, cold fronts advance at speeds up to 80 km per hour, about 50% faster than warm fronts. These two differences, steepness of slope and rate of movement, largely account for the more violent nature of cold front weather compared to the weather generally accompanying a warm front. As a cold front approaches, generally from the west or northwest, towering clouds can often be seen in the distance. Near the front, a dark band of ominous clouds foretells the ensuing weather. The forceful lifting of warm, moist air along a cold front is often rapid enough that the released latent heat increases the air's buoyancy sufficiently to render the air unstable. Heavy downpours and vigorous wind gusts associated with mature cumulonimbus clouds frequently result. Because a cold front produces roughly the same amount of lifting as a warm front, but over a shorter distance, the precipitation is generally more intense but of shorter duration, figure 9.6. A marked temperature drop and wind shift from the southwest to the northwest usually accompany frontal passage. The reason for the wind shift will be explained later in this chapter. The weather behind a cold front is dominated by subsiding air within a continental polar, CP, air mass. Thus, the drop in temperature is usually accompanied by clearing that begins soon after the front passes. Although subsidence causes adiabatic heating aloft, the effect on surface temperatures is minor. In winter, the long, cloudless nights that follow the passage of a cold front allow for abundant radiation cooling that produces frigid surface temperatures. By contrast, the passage of a cold front during a summer heat wave produces a welcome change in conditions as hot, hazy, and sometimes polluted MT air is replaced by crisp, clear CP air. When the air behind a cold front moves over a relatively warm surface, radiation emitted from Earth can heat the air enough to produce shallow convection. This in turn may generate low cumulus or stratocumulus clouds behind the front. However, subsidence aloft keeps these air masses relatively stable. Any clouds that form will not develop great vertical thickness and will seldom produce precipitation. One exception is the lake effect snow discussed in Chapter 8, in which the cold air behind a front acquires heat and moisture as it traverses a comparatively warm body of water. In North America, Cold fronts form most commonly when a continental polar air mass clashes with maritime tropical air. However, wintertime cold fronts can form when even colder, drier continental Arctic (CA) air invades a continental polar or maritime polar air mass. Over land, Arctic cold fronts tend to produce very light snowfalls because the continental polar air masses they invade are quite dry. By contrast, the passage of an Arctic cold front over a relatively warm water body may yield heavy snowfall and gusty winds. Table 9.2 shows the typical weather conditions associated with the passage of a cold front in North America. The eastern seaboard of North America is sometimes affected by another type of cold front, called a backdoor cold front. Most cold fronts arrive from the west or northwest, whereas backdoor cold fronts come in from the east or northeast, hence their name. Driven by clockwise circulation from a strong high-pressure center over northeastern Canada, colder, denser maritime polar, MP, air from the North Atlantic displaces warmer, lighter air over the continent, as shown in Figure 9.7. Backdoor fronts are primarily springtime events that tend to bring cold temperatures, low clouds, and drizzle, although thunderstorms occur occasionally. Backdoor cold fronts are less frequent in summer, but when they occur, the cool air can provide welcome relief from midsummer heat waves in the northeastern United States. Stationary fronts. Occasionally, airflow on both sides of a front is neither toward the cold air mass nor toward the warm air mass. Rather, it is almost parallel to the line of the front. Consequently, the surface position of the front does not move, or it moves sluggishly. This condition is called a stationary front. On a weather map, a stationary front is shown with blue triangles pointing into the warm air and red semicircles pointing into the cold air, see Figure 9.2a. Because some overrunning usually occurs along stationary fronts, gentle to moderate precipitation is likely. Stationary fronts may remain over an area for several days, in which case flooding is possible. When stationary fronts begin to move, they become cold or warm fronts, depending on which air mass advances. Occluded fronts. The fourth major type of front is the occluded front, in which a rapidly moving cold front overtakes a warm front, as shown in Figure 9.8a, b. As the cold air wedges the warm front upward, a new front forms between the advancing cold air and the air over which the warm front is gliding, a process known as occlusion, Figure 9.8b. The weather of an occluded front is highly variable. Most precipitation is associated with the warm air that is being forced aloft, Figure 9.8c. When conditions are suitable, however, the newly formed front is capable of initiating precipitation of its own. There are two types of occlusion, cold-type occluded fronts and warm-type occluded fronts. In the occluded front shown in Figure 9.9a, the air that had been behind the cold front is colder than the cool air it is overtaking. This is the most common type of occluded front east of the Rockies and is called a cold-type occluded front. Cold-type occluded fronts frequently produce thunderstorms and thus resemble cold fronts in the type of weather generated. It is also possible for the air behind an advancing cold front to be warmer than the cold air it is overtaking. These warm-type occluded fronts, figure 9.9b, frequently occur along the Pacific coast, where milder maritime polar air invades more frigid polar air that had its origin over the continent. Because of the complex nature of occluded fronts, they are often drawn on weather maps as either warm or cold fronts, depending on what kind of air is the aggressor. Sometimes, however, an occluded front is drawn as a purple line with alternating purple triangles and semicircles pointing in the direction of movement. Drylands. Classifying fronts based solely on the temperature differences across the frontal boundary can be misleading. Humidity also influences the density of air. All other factors being equal, humid air is less dense than dry air. In the summer it is not unusual for a southeastward moving air mass that originated over the northern Great Plains to displace warm, humid air over the lower Mississippi Valley. The front that develops is usually labeled a cold front, although the advancing air may not be any colder than the air it displaces. Simply, the drier air is denser and forcefully lifts the moist air in its path, much like a cold front. The passage of this type of frontal boundary is noticeable as a sharp drop in humidity, without an appreciable decrease in temperature. A related type of boundary, called a dry line, develops most often over the southern Great Plains. This occurs when dry, continental tropical, CT, air originating in the southwest meets moist, maritime tropical, MT, air from the Gulf of Mexico. Drylands are spring and summer phenomena, that most often generate a band of severe thunderstorms along a line extending from Texas to Nebraska that moves eastward across the Great Plains. A dry line is easily identified by comparing the dew point temperatures of the CT air west of the boundary with the dew points of the MT air mass to the east, figure 9.10. Midlatitude cyclones and the polar front theory. Midlatitude cyclones are low-pressure systems with diameters that often exceed 1,000 km and travel from west to east across the middle latitudes in both hemispheres, see figure 9.2. Lasting from a few days to more than a week, a midlatitude cyclone in the northern hemisphere has a counterclockwise circulation pattern with airflow directed inward toward its center. Most mid-latitude cyclones have a cold front and a warm front extending from the central area of low pressure. Surface convergence and ascending air initiate cloud development that frequently produces precipitation. As early as the 1800s, cyclones were known as the bearers of precipitation and severe weather. Thus, the barometer was established as the primary tool in forecasting day-to-day weather changes. However, this early method of weather prediction largely ignored the role of air mass interactions in the formation of these weather systems. Consequently, it was impossible to determine the conditions under which cyclone development was favorable. The first comprehensive model of cyclone development and intensification was formulated by a group of Norwegian scientists during World War I. German influence restricted the Norwegians from receiving international communications, including critical weather reports pertaining to conditions in the Atlantic Ocean. To counter this deficiency, a closely spaced network of weather stations was established throughout Norway. Using this network, these Norwegian-trained meteorologists made great advances in broadening our understanding of the weather and, in particular, weather associated with a mid-latitude cyclone. Included in this group were Wilhelm Bjerknes, pronounced Byrknes, his son Jacob Bjerknes, Jacob's fellow student Halvor Solberg, and Swedish meteorologist Tor Bergeron, see box 5.2. In 1921 the work of these scientists resulted in a publication outlining a compelling model of how mid-latitude cyclones progress through stages of birth, growth, and decay. These insights, which marked a turning point in atmospheric science, became known as the polar front theory, also referred to as the Norwegian cyclone model. Even without the benefit of upper air charts, these skilled meteorologists presented a model that remains remarkably applicable in modern meteorology. In the Norwegian cyclone model, mid-latitude cyclones develop in conjunction with polar fronts. Recall that polar fronts separate cold polar air from warm subtropical air, see Chapter 7. During cool months polar fronts are generally well defined and form a nearly continuous band around Earth recognizable on upper air charts. At the surface, this frontal zone is often broken into distinct segments separated by regions of gradual temperature changes. It is along these frontal zones that cold, equatorward moving air collides with warm, poleward moving air to produce most mid-latitude cyclones. Students sometimes ask, what is an extratropical cyclone? Meaning outside the tropics, extratropical is simply another name for a mid-latitude cyclone. The term cyclone refers to the circulation around any low-pressure center, regardless of its size or intensity. Hence, hurricanes and mid-latitude cyclones are two types of cyclones. Whereas extratropical cyclone is another name for a mid-latitude cyclone, the name tropical cyclone is often used to describe a hurricane. Life cycle of a mid-latitude cyclone. According to the Norwegian model, cyclones form along fronts and proceed through a generally predictable life cycle. This cycle can last from a few days to more than a week, depending on atmospheric conditions. One study found that more than 200 mid-latitude cyclones form in the Northern Hemisphere annually. Figure 9.11 shows 6 stages in the life of a typical mid-latitude cyclone. The first stage in this process is called cyclogenesis, meaning cyclone formation. Formation, the clash of two air masses. A mid-latitude cyclone is born when two air masses of different densities, temperatures, are moving roughly parallel to a front but in opposite directions. In the classic polar front model, this would be continental polar air associated with the polar easterlies on the north side of the front and maritime tropical air driven by the westerlies on the south side of the front. Under suitable conditions the frontal surface that separates these two contrasting air masses becomes wave-shaped and is usually several hundred kilometers long, figure 911b. These waves are similar to, but much larger than, the waves that form on water. Some waves tend to dampen, or die out, whereas others grow in amplitude. As these storms intensify, or deepen, the waves change shape, much like a gentle ocean swell does as it moves into shallow water and becomes a tall, breaking wave, figure 911c. Development of cyclonic flow. As a wave evolves, warm air advances poleward to form a warm front, while cold air moves equatorward to form a cold front. This change in the direction of the surface flow is accompanied by a readjustment in the pressure pattern and results in somewhat circular isobars, with the lowest pressure located at the crest of the wave. The resulting flow is an inward-directed, counterclockwise circulation that can be seen clearly on the weather map shown in Figure 9.12. Once the cyclonic circulation develops, general convergence results in forceful lifting, especially where warm air is overrunning colder air. Figure 9.12 illustrates that the air in the warm sector, over the southern states, is flowing northeastward, toward cooler air that is moving toward the northwest. Because the warm air is moving perpendicular to the front, we can conclude that the warm air is invading a region formerly occupied by cold air. Therefore, this must be a warm front. Similar reasoning indicates that to the left, west, of the wave front, cold air from the northwest is displacing the air of the warm sector and generating a cold front. Mature stage of a mid-latitude cyclone. During the mature stage of a mid-latitude cyclone, the pressure surrounding the low continues to drop, causing winds to strengthen and frontal weather to develop. The weather can be quite varied, depending on the season and one's location in relation to the cyclonic storm. In winter, for example, a place directly north of a strong mid-latitude cyclone might experience heavy snowfall and blizzard-like conditions, whereas the weather ahead of the warm front may be freezing rain. Occlusion, the beginning of the end. Usually, a cold front advances more rapidly than the warm front. As it moves, a cold front begins to overtake, lift, the warm front, as shown in Figure 9.11d, e. This process forms an occluded front, which grows in length as the warm sector is displaced aloft. As occlusion begins, the storm often intensifies. However, as more of the warm air is forced aloft, the surface pressure gradient weakens, as does the storm itself. Within 1 or 2 days the entire warm sector is forced aloft, and cold air surrounds the cyclone at the surface, Figure 9.11f. Thus, the horizontal temperature, density, difference that existed between the two contracting air masses is largely eliminated. At this point the cyclone has exhausted its source of energy. Friction slows the surface flow, and the once highly organized inward-directed, counterclockwise flow ceases to exist. A simple analogy may help you visualize what happens to the cold and warm air masses in the preceding discussion. Imagine a large water tank that has a vertical divider separating it into 2 equal parts. Half of the tank is filled with hot water containing red dye, and the other half is filled with blue-colored icy cold water. Now imagine what happens when the divider is removed. The cold, dense water will flow under the less dense warm water, displacing it upward. This rush of water will come to a halt as soon as all of the warm water is displaced toward the top of the tank. In a similar manner, a mid-latitude cyclone dies when all of the warm air is displaced aloft and the horizontal discontinuity between the air masses no longer exists. Idealized weather of a mid-latitude cyclone. The Norwegian model is a valuable tool for interpreting mid-latitude weather patterns, so keeping it in mind may help you understand, and possibly anticipate, changes in daily weather. Figure 9.13 illustrates a mature mid-latitude cyclone. Note the distribution of clouds and thus the regions of possible precipitation. Compare this map to the satellite image of a cyclone in Figure 9.26. It is easy to see why we often refer to the cloud pattern of a cyclone as having a comma shape. Guided by the westerlies aloft, cyclones generally move eastward across the United States. Therefore, we can expect the first signs of a cyclone's arrival to appear in the western sky. Upon reaching the Mississippi Valley, however, cyclones often begin a more northeasterly trajectory and occasionally move directly northward. Typically, a mid-latitude cyclone requires 2 or more days to pass completely over a region. During that span, abrupt changes in atmospheric conditions may occur, particularly in late winter and spring, when the greatest temperature contrasts occur across the mid-latitudes. Using Figure 9.13 as a guide, let us examine these weather producers and the changes you might expect if a mid-latitude cyclone passed over your area. To facilitate our discussion, profiles of the storm are provided above and below the map. They correspond to lines AE and FG on the map. Remember that these storms move from west to east, therefore, the right side of the cyclone shown in Figure 9.13 will be the first to pass over the particular region. First, imagine the change in weather as you move from right to left along profile AE, see bottom of Figure 9.13. At point A, the sighting of cirrus clouds is the first sign of the approaching cyclone. These high clouds can precede the surface front by 1,000 km or more and are normally accompanied by falling pressure. As the warm front advances, lowering and thickening of the cloud deck occurs. Within 12 to 24 hours after the first sighting of cirrus clouds, light precipitation usually commences, point B. As the front nears, the rate of precipitation increases, the temperature rises, and winds begin to change from an easterly to a southwesterly flow. With the passage of the warm front, the area behind, west of, the front, called the warm sector, is under the influence of a maritime tropical air mass, point C. Depending on the season, the region affected by this part of the cyclone experiences warm to hot temperatures, southwesterly winds, fairly high humidities, and clear to partly cloudy skies containing cumulus or cumulus-cumulus clouds. The warm conditions associated with the warm sector pass quickly and are replaced by gusty winds and precipitation generated along the cold front. The approach of a rapidly advancing cold front is marked by a wall of rolling black clouds, point D. Severe weather accompanied by heavy precipitation, and occasionally hail or a tornado, can be expected. The passage of the cold front is easily detected by a dramatic shift in wind direction. The warm flow from the south or southwest is replaced by cold winds from the west to northwest, resulting in a pronounced decrease in temperature. Also, rising pressure hints of the subsiding cool, dry air behind the cold front. Once the front passes, the skies clear quickly as cooler, drier air invades the region, point E. A day or two of almost cloudless blue skies is often experienced, unless another cyclone is edging into the region. A very different set of weather conditions prevails in the portion of the cyclone located north of the center of low pressure, profile FG at the top of Figure 9.13. In this part of the storm, temperatures remain cool. The first hints of the approaching low-pressure center are a continual drop in air pressure and increasingly overcast conditions that bring varying amounts of precipitation. This section of the cyclone most often generates snow during the winter months. Once the process of occlusion begins, the character of the storm changes. Because occluded fronts tend to move more slowly than other fronts, the entire wishbone-shaped frontal structure shown in Figure 911 rotates counterclockwise. As a result, the occluded front appears to bend over backward. This effect adds to the misery of the region influenced by the occluded front because it lingers over the area longer than the other fronts. Box 9.1. Flow aloft and cyclone formation. The polar front model shows that cyclogenesis, cyclone formation, occurs where a frontal surface is distorted such that it takes on the shape of an ocean wave. Several surface factors are thought to produce this wave in a frontal zone. Topographic irregularities, such as mountains, temperature contrasts, as between sea and land, or ocean current influences can disrupt the general zonal, west to east, flow sufficiently to produce a wave along a front. In addition, a strong jet stream in the flow aloft frequently precedes the formation of a surface cyclone. This fact strongly suggests that upper-level flow contributes to the formation of these rotating storm systems. When the earliest studies of cyclones were conducted, few data were available on airflow in the middle and upper troposphere. Since then, correlations have been established between surface disturbances and the flow aloft. When winds aloft exhibit a relatively straight zonal flow, little cyclonic activity occurs at the surface. However, when the upper air begins to meander widely from north to south, forming high-amplitude waves of alternating troughs, lows, and ridges, highs, cyclonic activity intensifies. Moreover, when surface cyclones form, almost invariably they are centered below the jet stream core and downwind from an upper-level low, Figure 9.14. Cyclonic and anticyclonic circulation. Before discussing how surface cyclones are generated and supported by the flow aloft, let us review the nature of cyclonic and anticyclonic winds. Recall that airflow around a surface low is inward and leads to mass convergence, coming together. Because the accumulation of air is accompanied by a corresponding increase in surface pressure, we might expect a surface low pressure center to fill rapidly and be eliminated, just as the vacuum in a coffee can is quickly equalized when opened. However, cyclones often exist for a week or longer. For this to happen, surface convergence must be offset by outflow aloft, Figure 9.15. As long as divergence, spreading out, aloft is equal to or greater than the surface inflow, the low pressure can be sustained. Because cyclones are bearers of stormy weather, they have received far more attention than their counterparts, anticyclones. Yet the close relationship between them makes it difficult to totally separate a discussion of these two pressure systems. The surface air that feeds a cyclone, for example, generally originates as surface air flowing out of an anticyclone, Figure 9.15. Consequently, cyclones and anticyclones are typically adjacent to one another. Like a cyclone, an anticyclone depends on the flow aloft to maintain its circulation. In an anticyclone, divergence at the surface is balanced by convergence aloft and general subsidence of the air column, Figure 9.15. Box 9.1. Winds as a forecasting tool. Every wind has its weather. Francis Bacon, English philosopher and scientist, 1561–1626, people living in the middle latitudes know well that during the winter, north winds can chill a person to the bone, figure 9a. Conversely, a sudden change to a southerly flow can bring welcome relief from these frigid conditions. Especially observant people, or those who have completed a meteorology course, might notice that when the wind direction switches from southeast to south, foul weather often follows. By contrast, a change in wind direction from the southwest to the northwest is usually accompanied by clearing conditions. Just how are the winds and the forthcoming weather related? Modern weather forecasts require the processing capabilities of high-speed computers as well as the expertise of people with considerable professional training. Nevertheless, some reasonable insights into the impending weather can be gained through careful observation. The two most significant weather elements for this purpose are barometric pressure and wind direction. Recall that anticyclones, high-pressure cells, are associated with clear skies and that cyclones, low-pressure cells, frequently bring clouds and precipitation. Thus, by noting whether the barometer is rising, falling, or steady, we have some indication of the forthcoming weather. For example, rising pressure indicates the approach of a high-pressure system and generally fair weather. The use of winds in weather forecasting is also straightforward. Because cyclones are the villains in the weather game, we are most concerned with the circulation around these storm centers. In particular, changes in wind direction that occur with the passage of warm and cold fronts are useful in predicting impending weather. Notice in Figure 9.13 that with the passage of both the warm and cold fronts, the wind arrows change positions in a clockwise manner. For example, with the passage of the cold front, the wind shifts from southwest to northwest. From nautical terminology, the word veering is applied to a clockwise wind shift such as this. Because clearing conditions normally occur with the passage of either front, veering winds are indicators that the weather will improve. In contrast, the area in the northern portion of the cyclone will experience winds that shift in a counterclockwise direction, as can be seen in Figure 9.13. Winds that shift in this manner are said to be backing. With the approach of a mid-latitude cyclone, backing winds indicate cool temperatures and continued foul weather. A summary of the relationship among barometer readings, winds, and the impending weather is provided in Table 9a. Although this information is applicable in a very general way to much of the United States, local influences must be taken into account. For example, a rising barometer and a change in wind direction from southwest to northwest is usually associated with the passage of a cold front and indicates that clearing conditions should follow. However, in the winter, residents of the southeast shore of one of the Great Lakes may not be so lucky. As cold, dry northwest winds cross large expanses of open water, they acquire heat and moisture from the relatively warm lake surface. By the time this air reaches the leeward shore, it is often humid and unstable enough to produce heavy lake effect snow, see Chapter 8. Divergence and convergence aloft. Because divergence aloft is essential to cyclogenesis, a basic understanding of its role is important. Divergence aloft does not involve the outward flow in all directions, as in a surface anticyclone. Instead, the winds aloft generally flow from west to east along sweeping curves. How does zonal flow aloft cause upper-level divergence? One mechanism responsible for divergence aloft is a phenomenon known as speed divergence. Wind speeds can change dramatically in the vicinity of the jet stream. On entering a zone of high wind speed, air accelerates and stretches out, divergence. In contrast, when air enters a zone of slower wind speed, an air pile-up, convergence, results. Analogous situations occur every day on a toll highway. When exiting a toll booth and entering the zone of maximum speed, we find automobiles diverging, increasing the number of car lengths between them. As automobiles slow to pay the toll, they experience convergence, coming together. In addition to speed divergence, other factors contribute to divergence, or convergence, aloft. These include directional divergence and directional convergence, which result from changes in wind direction. For example, directional convergence, also called confluence, is the result of air being funneled into a restricted area. On an upper air chart, convergence occurs in regions where height contours move progressively closer together. Returning to our interstate highway analogy, convergence occurs where a crowded 3-lane highway is reduced to 2 lanes due to construction. Divergence, the opposite phenomenon, is analogous to the location where the 2 lanes change back to 3. The combined effect of these and other factors is that an area of upper air divergence and surface cyclonic circulation generally develop downstream from an upper-level trough, as illustrated in Figure 9.15. Consequently, in the United States, surface cyclones generally form downstream, east, of an upper-level trough. As long as divergence aloft exceeds convergence at ground level, surface pressures will fall, and the cyclonic storm will intensify. Conversely, the zone in the jet stream that experiences convergence and anticyclonic rotation is located downstream from a ridge, Figure 9.15. The accumulation of air in this region of the jet stream leads to subsidence and increased surface pressure and, hence, is a favorable site for the development of a surface anticyclone. Because of the significant role that the upper-level flow has on cyclogenesis, it should be evident that any attempt at weather prediction must account for the airflow aloft. This is why TV weather reporters frequently illustrate the flow within the jet stream. In summary, the jet stream contributes to the formation and intensification of surface low and high pressure systems. Changes in wind speeds and/or directions cause air either to pile up, convergence, or spread out, divergence. Upper-level convergence is favored downstream, east, from a ridge, whereas divergence occurs downstream from an upper-level trough. At the surface, below regions of upper-level convergence, are areas of high pressure, anticyclones, whereas upper-level divergence supports the formation and development of surface cyclonic systems, lows. Where do mid-latitude cyclones form? The development of mid-latitude cyclones does not occur uniformly over Earth's surface but tends to favor certain locations, such as the leeward, eastern, sides of mountains and along coastal areas. In general, mid-latitude cyclones form in areas where significant temperature contrasts occur in the lower troposphere. Figure 9.16 shows the areas of greatest cyclone development over North America and adjacent oceans. Notice that a prime site for cyclone formation is along the east side of the Rocky Mountains. Other important sites are in the North Pacific and the Gulf of Mexico. Mid-latitude cyclones that influence western North America originate over the North Pacific. Many of these systems move northeastward toward the Gulf of Alaska. However, during the winter months these storms travel farther southward and often reach the west coast of the contiguous 48 states, occasionally traveling as far south as Southern California. These low-pressure systems provide the winter rainy season that affects much of the west coast. Most Pacific storms diminish in strength as they cross the Rockies, but they often redevelop on the eastern side of these mountains. A common area for redevelopment is Colorado, but other sites exist as far south as Texas and as far north as Alberta, Canada. Cyclones that redevelop over the Great Plains generally migrate eastward until they reach the central United States, where they follow a northeastward or even northward trajectory. Many of these cyclones traverse the Great Lakes region, making it one of the most storm-ridden portions of the country. In addition, some storms develop off the coast of the Carolinas and tend to move northward with the warm Gulf Stream, bringing stormy conditions to the entire Northeast. Patterns of movement. Once formed, most mid-latitude cyclones tend to travel in an easterly direction across North America and then follow a more northeasterly path into the North Atlantic, Figure 917. However, numerous exceptions occur. Panhandle hook. One well-known storm pattern anomaly is known as a panhandle hook. The hook describes the curved path these storms follow, Figure 917. Developing in southern Colorado near the Texas and Oklahoma panhandles, these cyclones first travel toward the southeast and then bend and travel sharply northward across Wisconsin and into Canada. Alberta Clipper. An Alberta Clipper is a cold, windy cyclonic storm that forms on the eastern side of the Canadian Rockies in the province of Alberta, Figure 917. Noted for their speed, they are called clippers because in colonial times the fastest vehicles were small ships by the same name. Alberta clippers dive southeastward into Montana or the Dakotas and then track across the Great Lakes, bringing dramatically lower temperatures. Winds associated with clippers frequently exceed 50 km per hour. Because clippers move rapidly and remain great distances from the mild waters of the Gulf of Mexico, they tend to be moisture deprived. As a result, they do not drop large amounts of snow. Instead, they may leave a few inches in a narrow band from the Dakotas to New York over a span as short as 2 days. However, because these winter storms are relatively frequent occurrences, they make a significant contribution to the total winter snowfall in the northern tier of states. Nor'easter. From the mid-Atlantic coast to New England, the classic storm is called a nor'easter, see Figure 917. These storms are called nor'easters because the winds preceding them in coastal areas are from the northeast. They are most frequent and violent between September and April, when cold air pouring south from Canada meets relatively warm humid air from the Atlantic. Once formed, a nor'easter follows the coast, often bringing rain, sleet, and heavy snowfall to the northeast. Because the circulation produces strong onshore winds, these storms can cause considerable coastal erosion, flooding, and property damage. The popular book and movie The Perfect Storm was based on a true story of a fishing boat that was caught in an intense nor'easter in October 1991. A brief case study of a classic nor'easter is found in Chapter 8, page 232. Flow aloft and cyclone migration. Recall that the wavy flow aloft is important to the development and evolution of a surface cyclonic storm. In addition, the flow in the middle and upper troposphere strongly influences the rate at which these pressure systems advance and the direction they follow. Generally, surface cyclones move in the same direction as winds aloft at the 500 millibar level, but at about 1/4 to 1/2 the speed. Normally these systems travel at 25 to 50 km per hour, advancing roughly 600 to 1,200 km daily. The faster speeds occur during the coldest months, when temperature gradients are greatest. One of the most difficult tasks in weather forecasting is predicting the paths of cyclonic storms. We have seen that the flow aloft tends to steer developing pressure systems. Let us examine an example of this steering effect by seeing how changes in the upper level flow correspond to changes in the path taken by a cyclone. Figure 918a illustrates the changing position of a mid-latitude cyclone over a 4-day period. Notice in Figure 918b that on March 21, the 500 millibar contours are relatively flat. Also notice that for the following 2 days, the cyclone moves in a southeasterly direction. By March 23 the 500 millibar contours make a sharp bend northward on the eastern side of a trough situated over Wyoming, Figure 918c. Likewise, the next day the path of the cyclone makes a similar northward migration. Although this is an oversimplified example, it illustrates the steering effect of upper-level flow. Our example examines the influence of upper airflow on cyclonic movement after the fact. To make useful predictions of cyclone movements, accurate appraisals of changes in the westerly flow aloft are required. For this reason, predicting the behavior of the wavy flow in the middle and upper troposphere is an important part of modern weather forecasting. Anticyclonic weather and atmospheric blocking. Due to the gradual subsidence within them, anticyclones generally produce clear skies and calm conditions. Because these high-pressure systems are not associated with stormy weather, both their development and movement have not been studied as extensively as those of mid-latitude cyclones. However, anticyclones do not always bring desirable weather. Large anticyclones often develop over the Arctic during the winter. These cold high-pressure centers are known to migrate as far south as the Gulf Coast, where they can impact the weather over as much as 2/3 of the United States, Figure 919. This dense frigid air often brings record-breaking cold temperatures. Occasionally, large anticyclones persist over a region for several days or even weeks. Once in place, these stagnant anticyclones block or redirect the migration of mid-latitude cyclones. Thus, they are sometimes called blocking highs. During these events, one section of the nation is kept dry for a week or more while another region remains continually under the influence of cyclonic storms. Such a situation prevailed during the summer of 1993, when a strong high-pressure system became anchored over the southeastern United States and caused migrating storms to stall over the Midwest. The result was severe drought in the southeast and the most devastating flooding on record for the central and upper Mississippi Valley. See Severe and Hazardous Weather, page 260. Low-pressure systems can also generate a blocking pattern. These lows, called cut-off low-pressure systems, are literally cut off from the west to east flow in the jet stream, Figure 920. Without a connection to the prevailing flow aloft, these lows remain over the same area for days, often producing dreary weather and large quantities of precipitation. Case study of a mid-latitude cyclone. To visualize the weather one might expect from a strong late-winter mid-latitude cyclone, we are going to look at the evolution of a storm as it migrated across the United States during the latter half of March. Case study of a mid-latitude cyclone. To visualize the weather one might expect from a strong late-winter mid-latitude cyclone, we are going to look at the evolution of a storm as it migrated across the United States during the latter half of March. This cyclone reached the U.S. West Coast on March 21, a few hundred kilometers northwest of Seattle, Washington. Like many other Pacific storms, this one rejuvenated over the western United States and moved eastward into the Plains states. By the morning of March 23, it was centered over the Kansas-Nebraska border, figure 921. At this time, the central pressure had reached 985 millibars, and its well-developed cyclonic circulation exhibited a warm front and a cold front. During the next 24 hours, the forward motion of the storm's center became sluggish. The storm curved slowly northward through Iowa, and the pressure deepened to 982 millibars, figure 922. Although the storm center advanced slowly, the associated fronts moved vigorously toward the east and somewhat northward. The northern sector of the cold front overtook the warm front and generated an occluded front, which by the morning of March 24 was oriented nearly east-west, figure 922. At that point the storm produced one of the worst blizzards ever to hit the north-central states. While the winter storm was brewing in the north, the cold front marched from western Texas, on March 23, to the Atlantic Ocean, March 25. During its two-day trek to the ocean, this violent cold front generated numerous severe thunderstorms and 19 tornadoes. By March 25 the low pressure had diminished in intensity, 1,000 millibars, and had split into two centers, figure 923. Although the remnant low from this system, which was situated over the Great Lakes, generated some snow for the remainder of March 25, it had completely dissipated by the following day. Now that you have read an overview of this storm, let us revisit this cyclone's passage in detail, using the weather charts for March 23 through March 25, see figures 921 to 923. The weather map for March 23 depicts a classic developing cyclone. The warm sector of this system, as exemplified at Fort Worth, Texas, is under the influence of a warm, humid air mass having a temperature of 70 degrees Fahrenheit and a dew point temperature of 64 degrees Fahrenheit. Notice that winds in the warm sector are from the south and are overrunning cooler air situated north of the warm front. In contrast, the air behind the cold front is 20 degrees to 40 degrees Fahrenheit cooler than the air of the warm sector and is flowing from the northwest, as depicted by the data for Roswell, New Mexico. On the morning of March 23, little activity was occurring along the fronts. As the day progressed, however, the storm intensified and changed dramatically. The map for March 24 illustrates the highly developed mid-latitude cyclone. The extent and spacing of the isobars indicate a strong system that affected the circulation of the entire eastern two-thirds of the United States. A glance at the winds reveals a robust counterclockwise flow converging on the low. The activity in the cold sector of the storm just north of the occluded front produced one of the worst March blizzards ever to affect the north-central United States. In the Duluth Superior area of Minnesota and Wisconsin, winds up to 81 miles per hour were measured. Unofficial estimates of wind speeds in excess of 100 miles per hour were made on the aerial bridge connecting these cities. Winds blew 12 inches of snow into 10 to 15-foot drifts, and some roads were closed for 3 days, figure 924. One large restaurant in Superior was destroyed by fire because drifts prevented firefighting equipment from reaching the blaze. By late afternoon on March 23, the cold front had generated a hailstorm in parts of eastern Texas. As the cold front moved eastward, it affected the entire southeastern United States except southern Florida. Throughout this region, numerous thunderstorms were spawned. Although high winds, hail, and lightning caused extensive damage, the 19 tornadoes generated by the storm caused even greater death and destruction. The path of the front can be easily traced from the reports of storm damage. By the evening of March 23, hail and wind damage were reported as far east as Mississippi and Tennessee. Early on the morning of March 24, golf ball-size hail was reported in downtown Selma, Alabama. About 6:30 a.m. that day, the governor's tornado struck Atlanta, Georgia, where the storm produced its worst destruction. Damage was estimated at over $50 million, 3 lives were lost, and 152 people were injured. The 12-mile path of the governor's tornado cut through an affluent residential area of Atlanta that included the governor's mansion, hence the name of the storm. The final damage, hail and a small tornado, along the cold front was reported at 4 a.m. on March 25 in northeastern Florida. Thus, a day and a half and some 1,200 kilometers after the cold front became active in Texas, the front left the United States to vent its energy over the Atlantic Ocean. By the morning of March 24, cold polar air had penetrated deep into the United States behind the cold front, see Figure 922. Fort Worth, Texas, which just the day before had been in the warm sector, experienced cool northwest winds. Sub-freezing temperatures moved as far as northern Oklahoma. Notice, however, that by March 25, Fort Worth was again experiencing a southerly flow. We can conclude that this was a result of the decaying cyclone that no longer dominated the circulation in the region. Also notice on the map for March 25 that a high was situated over eastern Louisiana. The clear skies and weak surface winds associated with the center of a subsiding air mass are well illustrated here. You may have already noticed another cyclone moving in from the Pacific on March 25, as the earlier storm exited to the east. This new storm developed in a similar manner but was centered farther north. As you might guess, another blizzard hammered the northern plains, and a few tornadoes spun through Texas, Arkansas, and Kentucky, while precipitation dominated the weather in the central and eastern United States. In summary, this example demonstrates the effect of a spring cyclone on mid-latitude weather. Within 3 days, Fort Worth, Texas, temperatures changed from warm to unseasonably cold. Thunderstorms with hail were followed by cold clear skies. You can see how the north-south temperature gradient, which is most pronounced in the spring, generates these intense storms. Recall that it is the role of these storms to transfer heat from the tropics poleward. Because of Earth's rotation, however, this latitudinal heat exchange is complex. If Earth rotated more slowly, a more leisurely north-south flow would exist that might reduce the temperature gradient, in which case the mid-latitudes would not experience stormy weather. Severe and hazardous weather. The Midwest floods of 2008 and 1993. Floods are part of the natural behavior of streams. They are also among the most deadly and destructive of natural hazards. Flash floods in small valleys are frequently triggered by torrential rains that last just a few hours. See Severe and Hazardous Weather in Chapter 10, page 279. By contrast, major regional floods in large river valleys often result from an extraordinary series of precipitation events over a broad region for an extended time span. The Midwest floods of 2008 and 1993 are examples of the latter situation. Midwest floods, June 2008. June 2008 saw record-breaking floods in many parts of the Midwest. June was a very wet month across a significant part of this region, with numerous heavy rain events resulting in record flooding in Iowa, Wisconsin, Indiana, and Illinois. Rainfall totals were more than twice the average in many places. Martinsville, Indiana, for example, reported a total of 20.11 inches of rain for the month, an amount equal to about half its annual rainfall and more than double its previous record high for a single month. Rainfall totals were more than twice the average in many places. Martinsville, Indiana, for example, reported a total of 20.11 inches of rain for the month, an amount equal to about half its annual rainfall and more than double its previous record high for a single month. During the 2 months prior to the floods, the jet stream had regularly been dipping southward into the central United States, placing the favored storm track for rainy low-pressure centers over the Midwest. As a result, at least 65 locations in the Midwest set new June rainfall records, while more than 100 other stations had rainfall totals that ranked second to fifth on record. Prior to the heavy June rains, many of these stations had an exceptionally wet winter and spring. Soils that were already waterlogged provided no place for additional rain to go, forcing the flow across the surface and causing streams to rise. The June 2008 floods represented the costliest weather disaster in Indiana history, while Iowa suffered widespread losses, with 83 of its 99 counties declared disaster areas. 9 of Iowa's rivers were at or above previous record flood levels, and millions of acres of productive farmland, an estimated 16% of the state's total, were submerged. Residential and commercial areas were evacuated, mostly in Cedar Rapids, where more than 400 city blocks were underwater, Figure 9b. The list of affected towns and rural areas throughout the Midwest was astonishing. Many riverside communities were flooded when swollen streams breached levees that had been built to protect the towns, Figure 9c. Overall agricultural losses exceeded $7 billion, and property damages topped $1 billion. The Midwest regional floods of 2008 were the worst in 15 years. The Great Flood of 1993. Although flood levels in some parts of the Midwest in June 2008 were the highest ever recorded, the overall impact of this event did not approach that of the Great Flood of 1993. Perhaps the country's worst non-hurricane flooding disaster, the 1993 event caused an estimated $27 billion in damages, adjusted to $2007. Unprecedented rainfall produced the wettest spring and early summer of the 20th century for the upper Mississippi River Basin, Figure 9d. Soils throughout the Midwest were already saturated from ample rainfall in summer and fall 1992, and soils remained moist as winter began. This pattern continued into spring and summer 1993. Rainfall in the upper Mississippi River Basin during April and May was 40% higher than the long-term average. As the deluge continued through July 1993, much of the basin received precipitation between 2 and 3 times the norm. A stationary weather pattern over the United States was responsible for the Midwest's persistent drenching rains. Most of the showers and thunderstorms developed in the boundary area between cooler air over the northern plains and warm, very humid air over the south. This front oscillated north and south over the Midwest during much of June and July. Meanwhile, a strong high-pressure system, the Bermuda High, became anchored over the southeastern United States, blocking the progression of weather systems through the eastern half of the nation. Some of the individual station reports were nothing short of astounding. In northwestern Missouri, Skidmore reported 25.35 inches of rain in July, where normal July rainfall is about 4 inches. Alton, in northwestern Iowa, had July rains that totaled 20.41 inches, and Leon in south-central Iowa reported 20.68 inches. Rainfall totals such as these leave no doubt that the record-breaking flooding on the Mississippi and other rivers in the Midwest was directly related to the exceptional rainfall during the spring and early summer. A modern view, the conveyor belt model. The Norwegian cyclone model has proven to be a valuable tool for describing the formation and development of mid-latitude cyclones. Although modern ideas have not completely replaced this model, upper air and satellite data provide meteorologists with a more thorough understanding of the structure and evolution of these storm systems. Armed with this additional information, meteorologists have developed another model to describe the circulation of a mid-latitude cyclone. The new way of describing the flow within a cyclone calls for a new analogy. Recall that the Norwegian model describes cyclone development in terms of the interactions of air masses along frontal boundaries, similar to armies clashing along battlefronts. The new model employs a modern example from industry: conveyor belts. Just as conveyor belts transport goods or people from one location to another, atmospheric conveyor belts transport air with distinct characteristics from one location to another. The modern view of cyclogenesis, called the conveyor belt model, provides a good picture of the airflow within a cyclonic system. It consists of 3 interacting air streams, 2 that originate near the surface and ascend and a third that originates in the uppermost troposphere. A schematic representation of these air streams is shown in Figure 9.25. The warm conveyor belt, shown in red, carries warm, moist air from the Gulf of Mexico into the warm sector of the mid-latitude cyclone, Figure 9.25. As this air stream flows northward, convergence causes it to slowly ascend. When it reaches the sloping boundary of the warm front, it rises even more rapidly over the cold air that lies beyond, north of, the front. During its ascent, the warm, humid air cools adiabatically and produces a wide band of clouds and precipitation. Depending on atmospheric conditions, drizzle, rain, freezing rain, glaze, and snow are possible. When this air stream reaches the middle troposphere, it begins to turn right, eastward, and eventually joins the general west to east flow aloft. The warm conveyor belt is the main precipitation-producing airstream in a mid-latitude cyclone. The cold conveyor belt, blue arrow, is airflow that starts at the surface ahead, north, of the warm front and flows westward toward the center of the cyclone, Figure 9.25. Flowing beneath the warm conveyor belt, this air is moistened by the evaporation of raindrops falling through it. Near the Atlantic Ocean, this conveyor belt has a marine origin and feeds significant moisture into the storm. Convergence causes this air stream to rise as it nears the center of the cyclone. During its ascent, this air cools adiabatically, becomes saturated, and contributes to the cyclone's precipitation. As the cold conveyor belt reaches the middle troposphere, some of the flow rotates cyclonically around the low to produce the distinctive calm ahead of the mature storm system, Figure 9.26. The remaining flow turns right, clockwise, and becomes incorporated into the general westerly flow. Here it parallels the flow of the warm conveyor belt and may generate precipitation. The third air stream, called the dry conveyor belt, is shown as a yellow arrow in figure 925. Whereas both the warm and cold conveyor belts begin at the surface, the dry air stream originates in the uppermost troposphere. As part of the upper-level westerly flow, the dry conveyor belt is relatively cold and dry. As this air stream enters the cyclone, it splits. One branch descends behind the cold front, resulting in the clear, cool conditions normally associated with the passage of a cold front. In addition, this flow maintains the strong temperature contrast observed across the cold front. The other branch of the dry conveyor belt maintains its westerly flow and forms the dry slot, cloudless area, that separates the head and tail of a comma cloud pattern, figure 926. In summary, the conveyor belt model of a mid-latitude cyclone provides a three-dimensional picture of the major circulation of these storm systems. It also accounts for the distribution of precipitation and the comma-shaped cloud pattern characteristic of mature cyclonic storms. Students sometimes ask. Sometimes when there is a major flood, it is described as a 100-year flood. What does that mean? The phrase 100-year flood is misleading because it leads people to believe that such an event happens only once every 100 years. The truth is that an uncommonly big flood can happen any year. The phrase 100-year flood is really a statistical designation, indicating that there is a 1 in 100 chance that a flood of a certain size will happen during any year. Perhaps a better term would be the 1 in 100 chances flood. Many flood designations are re-evaluated and changed over time as more data are collected or when a river basin is altered in a way that affects the flow of water. Dams and urban development are examples of some human influences in a basin that affect floods. Mid-latitude cyclones in review. Fronts are boundary surfaces that separate air masses of different densities, one usually warmer and more humid than the other. As one air mass moves into another, the warmer, less dense air mass is forced aloft in a process called overrunning. The 5 types of fronts are warm front, cold front, stationary front, occluded front, and dry line. The primary weather producer in the middle latitudes is the mid-latitude, or middle latitude, cyclone. Mid-latitude cyclones are large low-pressure systems with diameters often exceeding 1,000 km that generally travel from west to east. They last a few days to more than a week, have a counterclockwise circulation pattern with a flow inward toward their centers, and have a cold front and a warm front extending from the central area of low pressure. According to the polar front theory, mid-latitude cyclones form along fronts and proceed through a generally predictable life cycle. Along the polar front, where 2 air masses of different densities are moving parallel to the front and in opposite directions, cyclogenesis, cyclone formation, occurs, and the frontal surface takes on a wave shape that is usually several hundred kilometers long. Once a wave forms, warm air advances poleward, invading the area formerly occupied by colder air. This change in the direction of the surface flow causes a readjustment in the pressure pattern that results in somewhat circular isobars, with the low pressure centered at the apex of the wave. Usually, the cold front advances faster than the warm front and gradually closes the warm sector and lifts the warm front. This process is known as occlusion. Eventually, all of the warm sector is forced aloft, and cold air surrounds the cyclone at low levels. At this point, the cyclone has exhausted its source of energy and the once highly organized counterclockwise flow ceases to exist. Guided by the westerlies aloft, cyclones generally move eastward across the United States. Airflow aloft, divergence and convergence, plays an important role in maintaining cyclonic and anticyclonic circulation. In cyclones, divergence aloft supports the inward flow at the surface during the colder months, when temperature gradients are steepest. Cyclonic storms move at their fastest rate. Furthermore, the westerly airflow aloft tends to steer these developing pressure systems in a general west to east direction. Due to the gradual subsidence within them, anticyclones generally produce clear skies and generally calm conditions. The modern view of cyclogenesis, called the conveyor belt model, consists of three interacting air streams, two that originate at the surface and ascend and a third that originates aloft.